Hello, my name is Marc-André. I'm a postdoc at Mila and McGill, and today I will be presenting our work titled ML-MR, Software for Nonparametric and Nonlinear Mendelian Randomization Estimation using Machine Learning. Instrumental variable estimation is a technique to estimate causal effects in the presence of unmeasured confounding. For example, we may want to estimate the causal effect of an exposure, like cholesterol levels, on an outcome, like heart disease. If we consider the correlational relationship, our estimate will be biased because of confounding factors like diet. In this example, diet has an impact on cholesterol, but may also have an effect on other factors, such as hypertension, that may also be related to heart disease independently from cholesterol levels. To estimate causal effects, we can use a fourth variable, depicted by the hammer in this figure, that modulates the exposure independently from confounders. Random treatment allocation in a clinical trial or genetic variants are examples of instruments. When genetic variants are used as instrumental variables, we talk about Mendelian randomization. The most common instrumental variable estimator is a two-stage least squares. In the first stage, the conditional expectation of the exposure given the instrument is estimated. Then, this model is used to obtain predicted values of the exposure that are independent from the confounders by assumption. In the second stage, a simple regression of the outcome on the predicted exposure from the first stage allows estimating the causal effect. The DeepIV algorithm illustrated on the right side of this slide can also be used. DeepIV is a two-stage procedure, and the two stages look a lot like the two SLS. The first stage estimates the conditional density of the exposure given the instrument. Any model that estimates the conditional density can be used for this stage, and we have implemented three options in ML-MR. For the second stage, we sample a predicted exposure given the instrument from the density model, and we can use this sample to train an outcome neural network that models the causal relationship. In this talk, we will focus on describing ML-MR, a software that provides high-quality implementations of machine learning instrumental variable estimators. Then, we'll characterize the performance of these models in settings that reflect MR studies using simulation models. We will also talk about practical considerations for using these methods in MR and the advantage they may bring over current methods. ML-MR has four main components. First, we provide a simulation module that implements models found in the MR literature. This enables head-to-head comparison of different IV estimators. We also provide an estimation module that currently implements two variants of DeepIV, a new estimator we call Quantile IV, and a deep feature instrumental variable estimator, which I often call DFIV. All models can be fit easily, either using a command line utility or programmatically, and we adhere to the best practices in training modern machine learning algorithms. Then we have the evaluation module that facilitates model comparison and their evaluation when the true causal function is known, such as in simulation settings. Finally, we provide a hyperparameter sweep tool that can use random sampling or grid search and fits models in parallel using multiprocessing. Here we can see how these models work in practice with example commands. The simulation model is convenient because it allows resampling easily and the simulation to get simulation replicates, and you can save the data as either CSV files or Python pickle files to share models easily with colleagues. The estimation module provides a very simple interface to the complex algorithms that are implemented. In this example on the top right, we fit Quantile IV using 12 quantiles to estimate the conditional density, and we use a TSV file as the input. We also automatically provide valid prediction intervals for these models using conformal inference to quantify uncertainty. The evaluation module can also be used to plot the fits from different models and compute metrics like the mean squared error to the true function. This is what's illustrated on the bottom left corner. Finally, the bottom right shows the hyperparameter sweep module that uses JSON configuration files to describe sweeps and generate an SQLite 3 database that's used to store the run parameters and the run status. This access to this database is shared by the multiprocessing processes in order to execute the sweep in parallel. To assess the performance of the IV estimators in a realistic MR scenario, we have considered a simulation setting where we have a quadratic causal relationship and 20 genetic variants we use as IVs. The allele frequency of these variants is sampled randomly and is between 20 and 45%, and the fraction of the variance in the exposure that they explain is exposed as a simulation parameter. The other simulation parameters we vary are the population size, which goes from 10,000, 100,000, and 1,000,000 individuals, and the confounding strength by varying the causal effect that the confounder has on the exposure. Here we show the best models mean squared error across hyperparameter sweeps for all of these simulation configurations. We have compared 4 different models. We compared deep IV using a Gaussian network for density estimation, deep IV using a more flexible mixture density network for density estimation, the DFIV, and the quantile IV algorithms. Looking at the effect of varying the population size, we observed that DFIV and quantile IV are the best performing models across the board, as seen on this plot showing the MSE for the best model from a hyperparameter sweep. The box plots represent variation within simulation replicates. We also note that these models perform well even with a population size of 10,000 individuals. At large sample sizes, deep IV also performs well. Looking at the variance explained in the exposure by the instruments, we observe that DFIV and quantile IV once again perform best, especially when the IVs explain 20% of the variance. With stronger instrument strengths, the deep IV using a Gaussian neural network as the density estimator also performs well. In this presentation, we'll skip the effect of varying the confounding strength, but all models also performed well. These simulation results are interesting. However, they only provide information on the best case because where we know the actual optimal model. A natural heuristic to select that model would be to pick the one with the lowest second stage validation error. However, using this strategy does not reliably identify the best model. In this plot, the top row shows the relationship between the MSE to the true function and the second stage validation loss. We see that there is no correlation for both deep IV and DFIV. Interestingly, for these two models, we can see on the bottom plot that the conformal prediction interval width does predict the MSE quite well, and that selecting the model that has the smallest prediction interval width is a good strategy in this analysis. We also know that the conformal prediction interval in quantile IV is obtained differently than for the other two methods, which could explain why it behaves differently. For quantile IV, the model with minimal second stage loss typically also does very well with respect to the distance to the true function. Finally, we considered a more interesting simulation model that shows where these methods may bias something that the conventional estimators don't offer. We extended our simulation model by introducing an effect modifier variable m. The causal effect of the exposure on the outcome varies nonlinearly across strata of this variable. At low values of m, the effect is nearly null, whereas at high values of m, the effect is large. Within all strata of m, the causal effect remains linear. In other words, m only varies the slope of the causal relationship between the exposure and the outcome. This is actually a common setting. Think of the effect of a drug on a health outcome, but varying across a drug response modifier variable. Interestingly, when we use quantile IV to fit this model, we get a very high performance, as we can see in the bottom plot, where the quantile IV estimates in black track the true causal function in red at different levels of m. To conclude, MLMR is the first software package that provides a user-friendly implementation of machine learning instrumental variable estimators for Mendelian randomization. Here we have characterized the performance of the IV estimators in realistic MR scenarios, and we show the potential of machine learning IV estimators to estimate conditional treatment effects in the context of effect modification. In the future, we'll continue working to better understand how we can achieve optimal model selection, and we'll use this framework for drug target validation. Also note that MLMR is still under development, and we're constantly improving it and also trying to add additional algorithms. We would like to thank the organizers for giving us the opportunity to share this work, and I'd also like to thank my research supervisor, Joël Pinault, and my collaborators on this project, Arthur Yang, Michael Liu, and Jason Hartford. Don't hesitate to reach out online if you have questions about MLMR, and thank you for your attention.